Okay, so let's look at our different collisions. So you experimented with the magnet in the sides of the carts hitting each other, and then you experimented with the Velcro sides hitting each other. So you've got your track in front of you, and your track has a cart sitting somewhere towards the middle, and it has a cart. Hopefully you've got him over here, like to the side. I'm going to call that one 1 and this one 2. Now what I want you to do is give the one at the end of the track a little impulse so that it moves. Okay, all right, we need to all pay attention. Okay, so what did we notice that happened after the interaction with the magnet side? So we had, this was like magnet. They did repel each other, that's good. But what did the carts do? Okay, what did cart 1 do? Well, if we need to, your track is not level, I can see. But if we need to do it again, what'd you say? It looks like this, because what did 2 do? And 1 did what? Pretty much stopped. Okay, so 2 took off. Afterwards, moving at some other velocity, or some velocity. So this was the V1 initial, and this is V2 final. So if the force on cart 1 is equal and opposite to the force on cart 2, then momentum must be conserved based on Newton's third law. So the final momentum of the system, or the initial momentum of the system, must be equivalent to the final momentum of the system. So if that's true, let's look at our carts. So both of them had a mass of m. So this has a mass of m, this has a mass of m, we've got a mass m and a mass m. So initially, what was the momentum of the system? M times V1 initial. And then afterwards, because cart 2 wasn't moving, so what's the momentum of something that's not moving? 0. Okay, so then afterwards, what was moving? Just the second one, and it was same mass cart, and that would be V2. The masses are the same, therefore, what can we conclude about the velocities of these two? They're the same. So the energy, let's look at the conservation of energy, and specifically, how is the energy stored in this cart system? Kinetic. Very good. So let's look at the initial kinetic energy and the final kinetic energy. Initially, what's moving in our system? 1, 2, or both? 1. So that would be 1/2 m V1 initial squared. Then what's moving after the interaction? 2. So that would be 1/2 same mass, and that would be V2 squared. So these two velocities are equivalent, so we could just call them V for simplicity's sake. So then 1/2 mv squared would be equal to 1/2 mv squared. So what is also conserved in that interaction? Energy, kinetic energy to be specific. So if I were to graph the final momentum versus the initial momentum of our system, what would you expect to see? The final momentum to the initial momentum? A slope of 1, because they should be equivalent. It's like y equals x. And then what about the final kinetic energy to the initial kinetic energy of the system. Right, if they're equivalent, it's a y equals x expression, and the slope should be 1. So in a interaction, in a collision in which energy is conserved along with momentum being conserved, we call an elastic collision. So momentum and kinetic energy are conserved. All right, so now I want you to flip the carts around and put the Velcro to Velcro. Let's look at that Velcro collision. So you got the track again. Put one of the carts here in the middle and leave it at rest for now. This will be our cart 2 for my little picture here, and cart 1 over here. And we've got these Velcro, so I'm going to use a V to represent Velcro. Give a little impulse to 1 so that it moves towards 2, and we'll call that a V1 initial. So we see the result is that on my track afterwards, we see cart 1 and cart 2 stuck together. And if they're stuck together and they're moving together, then what can we deduce about the speeds of each one of them? They would be the same. So I'm going to call this V final. Or we can write it as V1 final is equal to V2 final, right? Because they're the same. And because it's the speed of 1 and 2 together, I'm going to be kind of silly and call it V3. So I'll just have one symbol that I use for the combined mass velocity. I'm not adding the two masses to get V3, but I add the two masses to get V3. Adding the two velocities, no. Adding the two masses, yes. Okay. So then let's look at the conservation of momentum. Momentum is conserved if there are no external forces acting on our system. And we saw in the first collision where the cart 1 collided with cart 2 and cart 2 started moving and cart 1 stopped, we saw that the forces must be equal and opposite. All the momentum of one object was transferred to the other in that elastic collision. So there must not be really enough friction in our system to cause the momentum to of the two-cart system to look not constant. So if the initial momentum of the system is equal to the final momentum of the system, and before the collision, one mass was moving at V1 initial, but then afterwards, how much mass was moving? 2m was moving at my fancy V3, okay? So then the speed of the combination should be 1/2 of the initial. That's a 3, that's not a 2. Thank you for fixing that up. Okay. All right. Yeah. Yes. So what it really looks like is M V3 plus M V3. So then that would be 2M V3. Because they both have the same velocity afterwards that I'm calling V3. Now let's check on the energy. Was kinetic energy conserved during this collision? So what is the sum of the initial kinetic energy? 1/2, one mass moving at V1 initial squared. the final kinetic energy would be two masses moving at their new combined velocity, which was v1 initial divided by 2 squared, which simplifies to what? mv1 initial squared over 4. Are these two equal? So energy was not conserved in this interaction. It went to other things that were not part of our system. So are the carts only touching each other? No way. They're touching what? The track, which is touching the table, which is attached to the earth. And so there's all these interactions. And when they collided with the Velcro sides, did they actually touch each other? With the Velcro sides? Doesn't the Velcro interact? Okay, so there's some. Did you hear it? I heard them. But then when you have the magnet sides hit each other, the forces are equal and opposite, but it's like we've got these super duper awesome spongy invisible springs between the two of them that cause very little energy to be transferred out of the system. So much so that one stopped and two moved. Okay? So instead of elastic, what prefix means not? In. So an inelastic only momentum is conserved. Now the energy change, the change in kinetic energy, will be dependent on the mass relationship too, because if we had 1m collide with 2m and get 3m, our velocity is going to be even smaller afterwards, which means our kinetic energy would be even smaller afterwards. So there is it's not always an equal, it's not always the same change, okay? But if I were to graph the final kinetic energy of my system versus the initial kinetic energy of my system, what would that graph look like as compared to the elastic collision? So in this particular one, the slope would be like 1/2, but in general, what would you expect the slope to be? Slope would be less than 1. Now what I want you to do is turn one cart around so that you've got a magnet side colliding with a Velcro side. All right, put one in the middle. Put a cart in the middle and put one out to the side like we've done before. And now we're going to have magnet to Velcro. Do you think we're going to have any kind of interaction? We got magnet here, we got Velcro here. Magnets and Velcros don't stick together or bounce off of each other in particular. All right, so now give cart 1 an impulse. So what do you notice after that interaction? So we saw that they both moved afterwards. So they didn't stick together, but they didn't exchange, or there wasn't a conservation of energy because both of them were moving a little bit slower than the original. So one moved off to the right, and two moved off to the right with a slightly bigger velocity, v2, and this would be v1, and I really should draw this initial velocity of 1 much bigger, v1 initial. So this is not elastic. It's also not totally, completely 100% inelastic. It's somewhere in the middle. So it's still an inelastic collision because energy was not conserved. So this is still inelastic. But both carts can collide, both two objects can collide, and both can move afterwards at different velocities and energy still not be conserved. It depends on how the interaction and the collision occurred. So in real life, it's really, really, really difficult to have an elastic collision. We have some collisions that are really close to being elastic. So like when you drop a bouncy ball or something and it comes back up almost to where you dropped it from. Or you look at, in chemistry, when you study the kinetic theory of gases and the collisions and the pressure that's created on the inside of a container holding a gas is based on the collisions with the walls, and we assume that they are elastic because they're really, really small and they don't quite interact with each other before their electric fields cause them to bounce back off of each other, just like the magnetic fields cause those to bounce off each other. So it's really hard to get an elastic collision in real life. Inelastic collisions happen all the time. Totally, completely, 100% perfectly inelastic collisions where they stick together occur quite often. I know we watch football games and we watch other kinds of sports and things where people tackle each other or whatever, and when they grab each other and the two things are moving together, that was inelastic. It was totally inelastic, completely inelastic. They stick together. Okay, so there are two basic categories for collisions: elastic, energy, and momentum are conserved. Inelastic, not energy, but momentum is conserved. Okay.